Okay, so we have our plant, which is given, and we have our controller, which is given. And then to make things easier, we're gonna let k as a variable be equal to this numerator of our plant. That's just because it's a long number, but it's just gonna be a value to coefficient, obviously. And then our goal is to minimize z with this phase margin, which basically just means that we need to have a phase of -130 when we plug in a value for z. And this is an optimization problem, and we have two equations that we can create. We can create the magnitude equation, which is equal to 1 at some crossover frequency, obviously. And then we have our phase equation, which needs to be equal to -130 degrees, because our phase margin is 50, -130 is 50 degrees above -180, which is the definition of phase margin. And our magnitude needs to be equal to 1 at this phase, because your phase margin is analyzed at the crossover frequency. That's the definition of phase margin. So now we need the equation for our magnitude and for our phase. For the magnitude, you take all of these and you put them into the, you get the vector of it in the imaginary and real plane. So this is the same thing we'll do for the angles as well. What you'll do for the top one, you'll say, 5,000 root of 10, you have a vector that goes to that distance, k, and the magnitude of that is 5,000 root of 10. So that will stay the same. But for s plus 50, well, don't forget, s is equal to j omega n plus 50. So that can be represented like any other imaginary number, where we do like a plus b I. Like that's the same thing when you do s plus 50. When you do s plus 50, what you're really saying is 50 plus omega crossover I. That's what that really means when you want to get the magnitude. And so when you find your magnitude function, you're going to draw it like for your controller, your magnitude is 5,000 root of 10, or that's just k, right? We said we could do that. So k over the square root of your imaginary half plus your real half. And the reason why I'm doing that is because what this really is 50 plus omega ci is a vector. I can go, this is the real and this is the imaginary. I can go to the right 50 and I can go up omega c and I get a vector right here. And if I want to know the magnitude of that vector, it's just the square root of its sides, right? 50 squared plus omega c squared. That's why this is right there. And we'll continue this off and we'll go the root of omega c squared plus 100 squared. And then finally, we can multiply that by the controller, which would be the root of z squared plus omega c squared over omega c squared plus 1 squared. This is an inequality that we can now manipulate. Now we have two unknowns. We don't know z, we don't know omega c. But our phase is also going to be a function of omega c and z. So you can put them in terms of one another. Now you have two unknowns and two equations. I'm going to do a cut here. My ass looked huge in that last clip. But now let's get the phase equation. So we know our phase must be equal to a -130 in order to achieve the phase margin we want at the crossover frequency. So how do we find the phase? The phase is just equal to the sum of the phases of the numerator minus the sum of the phases of the denominator. That's like the definition, or the angles of each of the vectors of the denominator and the numerator. So, if we want to get that, we can look at the very first, we can look at, we're multiplying them together. So let's look at the numerator. 5,000 root 10 on the, imaginary versus real plane is just to the side. And that is going to be an angle of 0 degrees. The angle is with respect to the real axis. So we have 0. So for our numerator, we have 0, and then we have s plus z. So that would be, you're going to go z in the real axis and s in the imaginary direction. Remember, s is equal to omega c j in this example, because we're at the crossover frequency. And if you have a vector like this, and you want to know its angle, you can just do the tan of this angle is equal to, opposite over adjacent. The opposite will be the imaginary, and real will be in the bottom. So So you can do arctan of imaginary over real gets you your phase angle. And so plug that in here, you end up getting, arctan of your imaginary, which is just the crossover frequency over the real, which would be z. So you're gonna get omega c over z. So this is all your numerators. Now you do your denominators, so you're gonna subtract it by the sum of your denominators. You get, arctan of your imaginary, which is omega c, over your real, which is 50. You get plus, arctan of omega c over 100. Let me make sure this is still recording. Cool, can you still see it? Yes. I know my handwriting is probably small and hard to read. Then you have, arctan of omega c over finally 1. So now you have your two equations, which has two unknowns, z and omega c, You can now rewrite the equations in terms of, z is equal to some function of omega c. So let me write that out on this side of the board, off screen. I'm just gonna do the algebra to move it over. And it's not so terrible. You'll just you'll divide both sides by the root omega, this square root, put it over here, and then square both sides, move it, manipulate it so you have just plain old z as a function of omega c. It's also not so bad over here too, because you can you'll subtract arctan over here. You'll take the tan of all of this, and then you'll put 1 over and then omega c. But you'll see the algebra over here. Okay, so when you do the algebra, you manipulate this equation. It's not so terrible. I did it on like one sheet of paper each, and I wrote pretty big. You end up getting z is equal to the square root of all of your poles. Each term is squared, but when you do the algebra, you get rid of the square roots over k squared. Don't forget k squared is our our gain over here, our 5,000 root of 10. Just easier way to write it. And then minus omega c, and z, crossover frequency over tan of, and this is just negative of this all. This is all just arctan functions of your crossover over your reals, the same as before. And yeah, that's what you're gonna do. You're gonna then take it, put it into your calculator. When you go into your TI-84, you got your function number 1, you plug it all in, you'll make it, F1, which is, Y1, which will be Z, equal to your function, and then Y2 will be equal to your function as well. And when you plot it, you will get, there'll be, 2 lines, there'll be an intersection. You can go to menu, you can go to 6, analyze graph. You'll go to intersection, which is 4. You'll hit a lower bound. You'll pick an upper bound. And it will find your intersection, which will give you 104 as your crossover frequency X, and 35.6, which is your Z, which is Y. One important thing to note is that you'll need to change the window, because the way your TI-84 calculator is going to work is in its the whole function. These functions are very complex, and what you want to do is you'll want to go to window settings, number 1, and you'll want to define your X-min and your X-max, and your Y-min and your Y-max. But really, you care about the X, and how you do that is when you draw your phase diagram for this whole, for your phase. So you go into your phase angle versus your frequency. You're drawing it for this whole, and this will be 0, minus 90, minus 180. When you draw it for the whole function, you can draw this before you do any of the math. If you look, if you look at it, you know that you have the lag controller, which it says in the problem, and you can infer. You know that you have 1 hertz is right here. You know that means that your z is smaller. It's going to be greater than 1. But the only area where it's possible to even be at negative 180 is going to be, well, here, let me just draw it. So you're going to come in at 0. At 1 hertz, you're going to drop down to 90, and then you're back to 1 when you go back up to when your 0 acts in. So your first thing is that you're coming in at 0. Then at 1 hertz, your pole comes in. Your pole comes in, goes in at negative 90 until at some point you have your z where it's going to go back up, and then it's going to go down at 50, and then then down to minus, this would be a 50, this is 100, that's why it's at negative 90 and then negative 180. You know the only spot where you're going to get your negative 130 degrees is like somewhere around 100. So 100 is negative 180, 50 is 90. So you can just say like, okay, somewhere between like 60 and 120, I know for sure I'm going to have a phase margin of 50 or an angle of negative 130. And so that's going to be your bound when you make it in your window, so you can actually be able to do that analyze part of it. In theory, you should be able to put this into a system of equations as well in your calculator. However, I'm getting error. I'm getting argument error. I think it's because the functions are very complex. This happens to me sometimes. I don't know why that is, but this is how I would do it. I'd make these functions z in terms of yc. I ended that video by accident, but I get z in terms of omega c, and then I would plug it into my graphing calculator. I would make my window size defined by where I know in the domain will probably be, because I've drawn my my approximated phase angle versus frequency diagram, just because we know p is gonna be less than 100, but probably greater than 1, and so somewhere in here, and so we know the only spot where they both act in is after 50, because that's where your second pole comes in. And 100 is where it goes to negative 180, so it's around 100 in that kind of transient down to negative 180. And so yeah, that's how I do it.